For anyone that doesn't know what this guy or who this guy is that comes on stage right now, he is someone that has been doing rendering for at least 7 years. So he has a YouTube channel, and I'll link that to you guys. Alexander Sannikov. But he's been doing rendering for a long time. And game development as well, apparently. But mostly he seems to be interested in rendering. 7 years, yeah, 8 years. And he is the one that's going to talk about the rendering of Path of Exile 2. Not 1, 2. The improved rendering.
Probably gonna get quite intense.
Okay.
I guess brace yourselves. There's a lot of stuff. The first technique, let's just get right onto it. The first technique I want to talk to you about is flowing materials. It's a very basic technique that is used everywhere in our game.
That looks like Perla noise to me.
It's a pretty typical effect. So how do we do this? Well, let's break it down.
Must be Perla noise.
This is an effect that is driven by velocity maps. So the goal is to have a texture that flows according to some flow that we calculate from somewhere, provided as a texture, we calculate it. The way you usually try to do this is, what if you try to apply a displacement to a texture and then just keep increasing that displacement over time? Well, this is what it creates. It creates this nasty warped texture. You just cannot keep distorting the texture indefinitely. So how do we solve this problem? Well, the way this problem is solved is usually you have layers. So you see this layer appears, shifts a little bit, and then disappears. It fades in, shifts a little bit, fades out. And then if we apply 2 of these layers that shift out of sync with each other, you get a perfectly smooth transition from one to another. So you don't see how they actually fade.
So they...
But
wait, damn, that is cool. And so basically you can create lava like that. You could create lava and what else? Maybe like a swamp?
This technique has a downside that if you stare carefully enough, you can see the fading between these 2 layers, because when entire layer fades out and then the other layer fades in, you can see some sort of a transition. The way you can solve this is you can also apply some sort of a noise to each of these layers to create this more random looking, more organic looking transition, so that each layer flows, but instead of fading in and out entirely, it has some sort of noise applied to it.
And so basically it fades in with the noise and fades out.
Then it looks much smoother. It looks like much smoother transition.
Damn.
So we use this for lava, for water, for any sort of liquid, basically.
We could use that for water, yeah.
By the way, for this specific technique, I prepared a shader toy demonstration because I very frequently I'm asked this question: how do I start programming graphics? Like, what do I do if I want to start graphics programming? Well,
the UV, he gets the UV, that's normal. Pretending he understands, I have absolutely no idea how to understand that. That is cool. Going to put the link there as well. Okay, let's continue.
Well, I always answer that, in my opinion, the best thing to learn graphics is just do graphics. Try programming shaders, and a great way to start programming shaders is get a shader that works. For example, this shader that I provided here that implements this effect, and just start hacking it. You can modify, you can see its effects on Shader Toy. Here's a link, and just experiment with it and learn this.
The only problem I have with Shader Toy, at least for me, it's not exactly the same as in GLSL, and therefore, like, I only know GLSL, and so I'm struggling there.
Called Subsurface Raymarching. Here's an example of what it allows to do. You're going to see a lot of Ranger because we typically use the modal for all our tests. So what is Raymarching? Raymarching is a process in computer graphics of rendering any sort of volumetric material. So when you have fog, when you have water, when you have some sort of material that transmits light and doesn't block it entirely. Challenges of Raymarching is that it usually involves some sort of a loop. When you Raymarch through a volume, you need to apply light, you need to calculate lighting for every step of your ray.
That could be,
and that's typically very expensive. But you can see that a lot of games still do this, because if you have to render a volume, there is nothing else you can do, so you do this anyway. But there is a better way. What if we Raymarch in a texture space instead? Then we don't need to store actually a 3D volume data. We can just use a single 2D texture and derive multiple layers from it. So here's an illustration how this can work. Blue is a view ray, orange is a surface that we are rendering, and there is a bunch of parallel planes that are subsurface planes. So we can calculate texture coordinates for these subsurface planes, and if we align them together, they look like a volume. So here's an example of what it looks like. like. For example, you see multiple volumes of water, sort of debris floating.
And that's just a 2D
you see the
texture.
Nice parallax between them. Another example.
Damn.
You can also do a bunch of effects.
Holy shit. What? They basically like look through this thing and then they create layers where they texture stacked on top of each other, like merge. Like it's basically a bunch of layers in Photoshop and then they merge down, right?
They all look like there is multiple surfaces, but they are all actually one surface, and the look of multiple surfaces is created in the shader by introducing multiple layers that are blended in the shader. Some more examples. This is a life orb that we planned to use for the UI, but unfortunately it's making an ExcelCon. But you can go further. The thing that you can also do is you can use data that is already present on your screen to calculate color of each volume. And what it allows is it allows you to calculate lighting of a surface only once and then reuse that information multiple times to render multiple layers. This is how we can render stuff like fur. And actually this technique I noticed is used in quite a lot of games recently, but I don't think it has like enough academic weight so that people publish papers about it. Different companies keep using similar techniques, they keep inventing similar clever techniques, but nobody really talks about them because, well, I don't know why. I just think these
maybe they don't want people to know.
And they're worth knowing about. Another example is some bear with an isotropic lighting model. Some more experiments with the Ranger. The way these techniques function is they rely heavily on this transformation called TBN. TBN is a basis that allows us to translate small steps in world space into small steps in UV space. So this way, when we are Raymarching a world ray, we can also calculate small offsets in a texture. It's used in lots of other techniques such as parallax mapping, etc., etc. It's not like a new invention, but if you are interested in computer graphics, I really advise you to familiarize yourself with this technique just because of the huge range of effects you can implement with it.
This is crazy.
Next technique I want to discuss, by the way, uses TBN base as well, is called Subsurface Shadows. This is an example of a technique that allows to render translucent sort of shadows. So like imagine, for example, if there is a shadow in smoke, you don't see a hard shadow, it gets blurred along the light direction. And typically, in order to simulate these shadows, you again need to employ volume rendering, which can be quite expensive. But there is a much cheaper way. And the way this can be done, the reason why it can be implemented in this way is because typical shadow map implementation involves an operation called percentage closed filtering, which is a loop that samples texture in a small radius to create this blurry look. But if there is already a loop, the cost, the expensive part of a shadow mapping operation is already paid. So we have come up with this idea of what if we use the same loop to also Raymarch along the ray and also blur the shadow not only in a radius but in depth as well. And this is basically how it works. You can create for free because the cost is already paid of PCF. The cost is already paid. We can just spread our samples instead of spreading them in radius, just spread them along a ray. You get this translucent effect for free. Next technique that we have employed, we call contact parallax. This is an example of what it looks like. A very typical problem that comes with artists
really super cool. That's what you are interested in.
Parallax, because artists love parallax, obviously, is that in order for parallax surfaces to intersect with each other, you need to either write fragment depth for each fragment of a parallax surface, or do something similar, but it's very expensive, because if a fragment writes depth, the shader becomes very expensive.
It's just a texture that's
blended.
However,
there is a much better way that avoids writing depth. Oh, by the way, another significant drawback of writing depth, it also creates nasty aliasing, because when a parallax map surface intersects with another surface, it creates nasty aliasing that is very hard to get rid of. But there is a much better way. What if you just get rid of the depth test, and what if you just fade surfaces? So here's an example of a surface here's an example of a surface. Yellow is a surface, and it intersects with this ground, black ground here. But instead of applying depth test that creates this harsh intersection line between parallax surface and the ground, what if you just apply a smooth transition from one to the other?
You're already doing that, right? Yeah, you're already doing that. You are basically merging this texture together with this one. You're already doing this. But you're doing it. You're merging the textures. I think in their case it's just a texture, and in your case, it is an actual 3D model.
Nicer effect, basically again for free. So you see, this allows us to blend parallax surface into ground that creates a much nicer transition. Again, this is a technique that is kind of at some point, well, in some sense it's obvious, but nobody really talks about it because I guess people consider it too obvious. I'm not sure. I know that a lot of other games do this same thing. Like I noticed Diablo 4 does this, a bunch of other games do the same thing, but I've never seen a publication on it. So I think it's just worth discussing so that people get inspired by these ideas. Next. Technique was developed to solve
you're taking the height information, right? And then you're using that as like a key or as an identifier on how to like merge this with the background.
I think it's just worth discussing so that people get inspired by these ideas. Next. Technique was developed to solve a very prolific problem in POE specifically, and honestly in many other games. This is rendering decals. What is a decal? Decal is basically a flat surface that you want to make it look like it's sitting on the ground. A very typical problem that happens when you try to do this is your surface intersects the ground ever so slightly, and you get these nasty intersection lines when your surface, your decal, intersects the ground. And there is sort of workarounds that people employ to mitigate this problem. For example, lifting decals slightly above ground. There is another technique called projective decals that has a lot of drawbacks. It's also very expensive. So while thinking about, like, what do we do about this problem? You see, like, this nasty line. The reason why this line appears is because of depth test. Again, because when two surfaces intersect, only one of them wins, the one that is closer to you.
Same technique as before.
Either one surface wins the depth test, either the ground or the decal, and you always can see only one of them. So we asked ourselves, what if we just get rid of the depth test? And the better way to do this is if you just disable depth test completely and replace it again with smooth fade. This allows us to create a much nicer transition. But however, in order to mitigate the problem of surfaces having wrong parallax when they appear under the surface, we can also correct their UVs to a UV that they would have had if they were sitting perfectly on the ground. This is relatively easy to do. It's techniques, again, similar to parallax occlusion mapping. But this combination of correcting UVs to a UVs of a surface sitting perfectly on the ground, as well as disabling depth test, allows us to create basically perfect decals that have none of the drawbacks of the typical decals, and they're very easy for artists to set up. So here is how this decal intersects with the ground. You see it never sharply appears, it never sharply disappears, it never creates harsh transitions. It's very smooth, very easy to use for artists. And here's a side-by-side comparison, what it looks like on a player scale with and without this technique. And next technique that I think is worth discussing. Again, it's not exactly a novel technique. It's used actually pretty widely in compressing videos. Very typical thing that artists like to do is they build flipbooks of effects. So basically a flipbook is a bunch of frames, usually 16 or 9 frames of a certain animation that they flick through. And if you just flick through frames of an animation,
so basically
you see the transition from one to another, it looks like shifting, like interpolating sharply between frames. But the way to mitigate this is called motion vectors. You can distort source frame towards the destination frame, and you can distort the destination frame towards the source frame as they blend from one to another. And this way you can create a much smoother transition with very low frame rates. So this flipbook...
But that doesn't work with pixel art, right? That only works in 3D games. That is cool. So basically you have like this... It's basically a cheap particle system, right? It's a cheap particle system. if you have an artist or if you can do something like that, you get like all of these particles for free and they look awesome.
For example, has just 16 frames during the entire animation. But if we apply motion vectors to this, it can look much smoother.
Oh, yeah.
Like it's the same amount of memory used, but looks like a much smoother transition. The big question is always, how do you calculate motion vectors? And this question has no simple answer. There is no algorithm that gives you perfect motion vectors. They are even defined in a kind of sort of ambiguous way. So every game company that uses this technique has to basically reinvent their motion vectors in some sense. And I want to tell you how we do this. Another example of just 2 frames blending. So this is source frame, destination frame. You see how they smoothly blend into each other because of motion vectors. The way we do this is we build this hierarchical representation of motion vectors. First, we find motion vectors in a very low resolution way. So just a very coarse picture of what our motion vectors would look like on the left. Then on the right, you see more. We refine that representation of motion vectors, and we can adaptively find perfect motion vectors by stacking these levels of details of motion vectors. Here's an example. This is a source frame of some flipbook. This is the destination frame of a flipbook. We need to find motion vectors that translate this image into this image. Basically, we need to distort one image towards the other. Yeah. The way we are going to do this is first we are going to overlay them. Yeah. I'm showing the first frame in red here and the second frame in green here.
Wow,
and when you combine red and green, you get yellow. So if we apply perfect motion vectors to this image, it should get completely yellow. So let's try to yellow this image. First, we are going to apply a very rough, I think it's just 4x4 motion vectors displacement. And you see like these frames already kind of sort of match, but in a very crude way. Then I'm going to keep refining and adding higher and higher resolution motion vectors. And you see here the iterative process that converges these images together and finds finer refinements.
Is that done using AI?
And this is what it looks like when we apply the motion vectors to these 2 frames. You see a nice smooth transition from one frame to another frame.
He doesn't explain.
So this is a technique that we use well for all of skills, for flipbooks, for flames, for all that sort of VFX.
Holy shit, so basically they create a bunch of animation frames. And then they blur between them. And so they are not creating like some physical objects. Iterative process, so basically he refines them by hand. So basically all of their effects, and we could even inspect that using RenderDoc, they are all
another technique I want to discuss today is bent normal shadows. Here's what it looks like. Bent normal shadows on, bent normal shadows off. Here's the comparison side by side. On the left, bent normal shadows off, bent normal shadows on. The problem they're solving is that
I mean, you could see a little bit more detail here, I guess. If that's the on part, there's like darker areas here. It's more detail on the right. Like the more I look at it. Okay.
That when we have a texture of a material that contains in it some big geometry, for example, a normal map, this texture never encodes information about shadowing. So normal maps don't shadow themselves. If I put it this way. So how do we overcome this problem? How do we make it so that the micro details in a normal map also cast shadows onto each other? Well, actually, the answer is that the information needed for this is already encoded into the normal map. It's encoded in AO. Ambient occlusion is a map that encodes information about adjacent geometry to every point. And we can actually reuse that information to cast shadows. What if we use baked occlusion for this? The way it works is for every point we can define a cone that is guaranteed to not occlude any light that's coming from within this cone. Mm-hmm. The angle of this cone can be derived from AO, and the direction of this cone can be derived from a thing called bent normals. So bent normals basically for each surface point defines the direction that the light is most visible from. So this is the direction that you least expect to see a shadow from. So this this is obviously an approximation, but it's a pretty neat approximation because we can use even normals or LOD of a normal and mipmap of a normal for the bent normal direction. We can use AO for the angle of the cone to create self-shadowing for very cheaply. It's almost free, applying this thing to a shadow in a shadow shader. And this is actually the technique that we use for lighting on the POE UI. Like actually the UI is completely 2D, but all the shadows that you see from in-game light sources are done with bent normals.
Holy! Look at the slots.
It's completely 2D.
Look at the slots here.
Thing to a shadow in a shadow shader, and this is actually the technique that we use for lighting on the POE.
Look at that frame. Wow. I mean, Real Superco only has to do this if he wants to make a Diablo clone. So it's fine. It's fine.
UI, like actually the UI is completely 2D,
is not animated,
but all the shadows that you see from in-game light sources are done with bent normals. Next subject, GPU particles. GPU particles is, here's an example of what it looks like. This is one of the very early tests. Do you recognize the Ranger? The point of GPU particles is if you have a finite amount of time, for example, 1 frame, where would you rather spend this 1 frame worth of calculation, for example, 1 millisecond, on the CPU or on the GPU?
GPU.
Well, the answer is it really depends on what exactly you're calculating. For example, calculating gameplay is much more efficient on the CPU. You are much better off spending 1 millisecond calculating a gameplay code on the CPU rather than on the GPU. But GPU is really good for calculating very simple, very repetitive tasks in huge amounts. And particles is exactly that.
Oh, so we have to do that too.
That's why it's just very natural to calculate particle behavior on the GPU.
Yeah.
And also,
shader, right?
It comes with very nice benefits that particle systems have access to stuff that is only present on the GPU, such as depth buffer, so we can do a bunch of interesting things with it.
Oh,
we actually developed pretty intense, pretty in-depth GPU particle system that even allows some minor physics simulation. This is simulating some particles interacting with the ground. And we fully integrated with our graph editing system. So our materials are designed with these.
This looks like Unreal Engine. That looks like Unreal Engine, boys. Wait, let's go back 1 frame.
This is simulating some particles interacting with the ground.
They have Unreal Engine in their engine. FX Graph Editor. Let's take a screenshot of that and put that in Showcase. For research purpose. You know, just saving that for research purposes there. Okay.
And we fully integrated with our graph editing system. So our materials are designed with these graphs that VFX artists can use, just visually connect things. And we just implemented our GPU particles into the same pipeline. Here's another example of the GPU particle system. You see, now we can allow having many more particles.
They all have bloom,
like
it looks like.
2 orders of magnitude more particles in the same calculation time as before.
Wow.
Just because we have offloaded that calculation from the CPU onto the GPU. In the same amount of time, your GPU can calculate many more particles than your CPU.
You know, the crazy thing about this, they have depth testing, right? So you can make them transparent. Like, and they will disappear if they are behind something. You could do alpha blend, you could do all of that stuff. Damn.
Here's another example of GPU particles. And here's a bunch of
it's the snow.
Player skills. So you see when the meteor strikes or when the nova strikes, there is a whole bunch of particles attracted by the shockwave.
Yeah. I mean, it's not a new technique to do that on the GPU.
I'm not sure if it was shown yet, but this is a player skill with an ice shield, and these ice particles, they too reflect. They react to players moving. They react to attacks from monsters.
Holy shit! It's an insane amount of calculations.
Rendering water.
Ooh!
Last time we already discussed some things about rendering water related to flow maps. But in my opinion, the hardest part about rendering water is rendering specifically waves that wash up on the shore.
Yeah.
That is just so hard. If you look up on the internet how to render water or whatever articles, you can find like 1 million articles of how to render water surface of how to render rivers, but you will find no articles whatsoever about how to render beach waves, because it's so hard. Like, there is simply no accepted solutions like, look, here's how you do it, because it's good and it just works. Because
usually
all solutions to render that types of waves are either bad or really complicated. So today I want to tell you the way we do this. Just to give you the idea. This is the effect that I'm talking about. So basically, when waves wash up on the shore, they dissipate. It looks
like textures, but maybe not.
So the unfortunate part about this task is that there is almost nothing we can pre-calculate. Like, even approaching this task, like, what do they even do? It's a pretty complicated task. And there is a lot of moving parts. So one very important thing is when you need to solve such a complex task as rendering waves that wash up on the shore, it really helps to break it down into parts and try to make them as independent as possible. So for example, rendering water surface itself should be completely decoupled from constructing the geometry of water surface, because these two tasks can be solved completely independently, and they should be solved completely independently. It's just much easier to tackle them this way. Another thing that I sort of taken away from doing this is that there is going to be a lot of parameters, like controlling behavior of water. There is literally hundreds of numerical parameters. There is thousands of functional parameters, and the only way to deal with them is to limit the range of each parameter, basically to define the correct range that each parameter is allowed to have. So for example, distance can be only positive, right? Distance cannot be negative, etc. Basically just basic physical limitations. And you renormalize every parameter to have this correct range of 0 to 1, so that you can never have the temptation to have like, well, I would rather set this parameter to 1.3. No, just define a set range of parameters that are safe, that you guarantee your shader will always work correctly with, if your parameters are within this range. Well, let's break down how the shader works. So first, we break water into these zones. You see these parallel zones, and within each zone there is a layer
sine wave.
That carries one wave. I am here applying a noise to this wave that shapes it in the maximum possible amplitude. So this noise is just a sine wave that goes from -1 to 1. So the wave cannot be deformed any more than this. And this is very important. Let me show you why. Because if we apply 2 of these layers, you need these layers to never intersect with each other, because the shader only calculates 2 layers for any given point. And if we allow the waves to deform any more than this, then they would start overlapping and the shader would stop working. That's why I brought up the allowed range. So again, what happened here is there is one layer, then I color in a different way, then I overlay multiple layers, and you see we are already creating sort of a seamless thing that where one wave overlaps correctly with another wave. Next thing is we color it in a more natural way. Then we replace the sine wave dummy noise with just a texture noise that looks nicer. Yeah. Next step is we apply some sort of screening on top of each one of these layers. Then we apply distortion to make these layers more organic, and that's how we get the final effect, basically.
Okay, I didn't understand anything.
Just to get through this again, this is layers, then we overlap these layers, then we color them, then we apply more organic noise, more noise, and this is the final effect that you get. Next technique, and actually a lot of previous techniques, they all often intertwine. Like you see, most of these techniques use, for example, TBN bases. Most of these techniques use fields. So what is fields? Fields allow creating any sort of liquid-looking surfaces. Basically, when opacity of a surface is in some way connected to its normal map, which is almost the case for liquids. So whenever a liquid dissipates, it has like a vertical normal. When it doesn't dissipate, it has like a horizontal normal. So this basically allows creating sort of blobs.
There must be polar noise.
The way field is not an our invention thing. They are widely used in all sorts of shader demos and demo scene. It's a very popular technique. But for some reason, well, it rarely gets into the hands of artists. Like demo sceners use this thing all the time, but for some reason, VFX artists don't use it that often. And I decided, like, how can we expose it to artists? How can we give them this tool that allows them to create liquid surfaces? Basically, a field is, simply put, is just a value and the vector that says how much this value changes. So basically, it's a value plus its gradient. And then you can add these fields just by adding a value and its gradient. You can multiply them the same way how you add a value and the gradient, etc., etc. You can do all sorts of operations that you usually do with just a floating point value, but you can do them with a field. And this field carries information about a surface opacity and at the same time about the normal associated with the surface. So it basically allows conducting all sorts of surface operations with preserving correct normals that react correctly to light, that react correctly to rotations. Here's another example of fields, which is a Druid skill volcano. That's done with fields. Again, fields are integrated into our graph editor so that artists can basically utilize them. Here's another example, just some test effect with water.
I didn't understand the field part very well. He didn't explain what a field is. Is it like a volume?
That I want to discuss. Global illumination. What is global illumination? Well, global illumination is the process of light bouncing between surfaces. Here is what it looks like if this scene has global illumination on. Here's the same scene without global illumination off.
So basically like ambient light, but global illumination.
Light gets propagated from really bright areas into darker areas. And the way that this process works is each point of the scene casts light onto every other point of the scene. And every point of the scene receives light from every other point of the scene. And also each point of the scene can block light between
I've seen that with RTX cards.
This many-to-many interaction is just notoriously hard to calculate.
Yeah.
Calculating global illumination is
I've seen a bunch of sponsor scenes.
I dare to say it's the hardest problem in computer graphics. And actually calculating global illumination is relatively easy. There is an algorithm called path tracing. It's just the only problem is that it takes like minutes to render every frame. It's extremely slow. The hard part is calculating in real time, like in a game scenario. And there's a lot of typical ways that they solve this in the industry. And unfortunately, none of them really fit us. And we had to do better than that.
Yeah, let's wait until GPUs become more powerful.
Our solution that we talked about on the previous ExileCon was, dare I say, the first of its kind in the industry. We implemented POE, and POE was the first game that shipped with a screen space global illumination based on variance.
Wow,
and it was very novel at the time. But it had just a few drawbacks that really kept gnawing me in my sleep. I really wanted to solve them. And these drawbacks come primarily from the fact that our screen space shadows had very important properties that our global illumination didn't. And these properties is that parts of our screen space shadow algorithm that don't require much detail are calculated in a much lower resolution. So our shadows are implemented via these cascades. So you see the first cascade here has only low resolution part of each shadow. Second image has only higher resolution of the shadows. And the last part is a tiny bit that requires shadows to be calculated in the highest resolution. But it means that each of these can be calculated in vastly different resolutions, making it much cheaper to calculate this in a downscaled resolution,
pointing to the top
rather
left.
than if we were trying to calculate the entirety of the thing in the same highest resolution. So this is a very important property that our shadow mapping algorithm has that actually I still haven't seen any other game implement this in this way with cascaded shadow maps. And I really wanted to adapt this property to our lighting.
From his last talk.
So I wanted our GI, global illumination, to have this property as well. So the typical way people implement global illumination is with radiance probes. Radiance probes are these, you can think of them as tiny cameras that you put all around your level, your geometry, that take a cube map, basically a photo of what surrounds each point. And then you use that information and code it in these cube maps, in these light probes, to light any object. Basically, see if I'm standing here, I'm checking what's the nearest camera to me contain. It contains this cube map. I'm applying this lighting to myself. Here, this is an approximation of global illumination. But the big question to ask here is, how many of these cameras do I need? What resolution do I need to use for each of these probes? And you can see that every game development studio comes up with their own answer. Some game development studios use lots of tiny probes. Other game development studios use a lot of much fewer, much higher resolution probes. And it seems like there is no answer. But what if we use them all? What if we create a hierarchy? When we have both high-resolution probes, but very few of them, and we use another grid with much more probes, where each probe is much,
like with the lighting,
much lower resolution. This is what I call radiance probe hierarchy. I was struck with this idea, and I just needed to implement this. Implementing this 3D was very hard, so I just decided to do a 2D.
This, by the way, if you're curious, is on his YouTube, as far as I remember. Yeah, that's on his YouTube, Global Illumination.
Test. By the way, 2D global illumination is almost as hard as 3D global illumination, so I just decided to test in 2D. Those of you who subscribe to my YouTube channel, you might have seen this experiment, where this is 2D global illumination, basically works perfectly. Like, this idea worked perfectly on the first implementation, which never happened. Here is a breakdown of how it works. You can see that there is these cascades, that each cascade contains a different number of rays, which corresponds to different resolution of the light probe. And if I change the cascades, they converge to proper lighting. So
why are you doing that? Why are you
this is final image, and this is how it's constructed from these cascades. Well, let's see in closer detail how these cascades work. On the left, you see a grid of cascades, grid of probes, where each probe casts just 4 rays. So you see, like, 4 rays from this probe, 4 rays from this probe, etc. Just a grid of probes. The right cascade contains fewer probes, but each probe casts more rays. But the question is, how many rays do we get if we combine these 2 cascades?
Isn't it a plus?
It gets very messy. You cannot really read easily what's happening on the left image, just what happens when I combine the probes. But if you look at every individual probe, we can see that we can actually construct 8 rays per probe. These rays are not perfect, they are slightly bent. You see, well, rays are normally straight lines, right? But these rays are slightly bent. However, if we make these segments shorter, they will start approximating lines more and more perfectly. So we can actually, this thing converges to perfect rays. But there is 8 rays per probe, and there is 16 probes. So the first image contains 64 segments. The second one contains 32 segments. But when we combine them, we can create 128 rays total. Well, this is curious. This means that if we increase the number of these cascades, so I have just shown 3, right? The number of rays that we cast with increasing number of cascades is 64, 128, 256, it's power of 2. But the total cost for calculating these cascades approaches a constant. We can calculate 100 cascades at almost the same cost as we calculate one cascade, because each next cascade is cheaper than the previous one.
Holy shit.
When I first realized this fact,
that's insane, yeah.
Mine was blown. Because this is a property that you see in no other rendering approach out there.
How are people so good at this?
Like this. This means
you get demoralized, bro. Ravini, dude, don't get demoralized. Let me quickly show you why this guy is so good, okay? That's his YouTube channel. If you scroll down all the way to the very beginning, he's been doing this not only 8 years, he's been doing this for 13 years. He's been working on stuff like that for 13 years. That's how you get so good at it. You don't have to have this super brain, okay? Don't think so. You just get good at it by just doing that. I'm on my 3rd year Like, imagine what 10 more years of experience does to you. It's insane.
The number of rays increases exponentially with the number of cascades that we use.
Damn.
And the total cost of infinite number of cascades is bound. It's less than a constant. Like, what? But this is literally what it is. This is what I learned when I implemented the first 2D version of GI. Rays get exponentially cheaper with more cascades. So the more rays you have, the cheaper they get.
That's
but this
insane.
is literally what it is.
You get it?
Well, I was quite excited when that 2D demo worked. Obviously, the next question was, how do I adapt this to POE? Because POE is 3D, and the implementation of it was my first implementation was 2D. Well, long story short, we did get there. We did implement this algorithm in 3D. Here is how it works. This is the first cascade. You see it captures information about only in tiny vicinity of each point. Basically, it looks like bad AO that you typically see in games. Next cascade captures longer field information, and it's lower frequency. Next contains even lower frequency, and so on. So we create this hierarchy of probes, where each level of hierarchy captures only a specific range of radiance of light, basically.
It looks insane.
But then the magic happens when we combine them all.
Oh my god!
Because this way we can get details of
Mr.
all
Super Cool, you have to do that.
From fine details to very long distance details in the same image by combining information from all of the hierarchy. This is how we encode, for those you graphics programming aficionados, this is how we encode screen space probes, basically in these tiny grids. You can see that this level contains these tiny probes, there is a lot of them. And this level contains much larger probes, and there is much less of them. But the memory that each layer, that each cascade level contains actually decreases the more cascades you have. So the first cascade is the more expensive one. Weirdly enough, the cascade that contains the tiniest bit of occlusion is the most expensive one.
Not POE2, that's Path of Exile 2, bro.
You have.
Look at Path of Exile 2.
Here is the implementation of the same technique in 2D. So the previous one, I always implement these like highly experimental, 90% gonna fail techniques in my like test bed pet engine. But then I implemented in POE. So this is again Glowing Ranger, classic, lighting the scene with only indirect light. I should have probably mentioned this before, but calculating light from emissive surfaces is computationally equivalent to calculating light from directly lit surfaces. It's basically the same thing for a GI. That's why it's very typical to test global illumination algorithms by just having
So essentially
objects.
you can do everything in global illumination now. You don't need any light sources anymore.
Implementation that we have in game uses screen space information. It uses screen space probes. But actually, it can also be used in, for other games. It might be more appropriate to use the same hierarchy of cascades in world space. And this demo that I also posted on my channel actually does just that. It has no screen space information. It's fully world space information, which means that it can calculate light sources behind the camera, which we don't have in POE, which we don't need to worry about. By the way, this technique, since it basically allows encoding light reaching every point from every direction.
Otherwise,
you can also use it to calculate specular, so basically reflections. So here you see one of the dungeons basically made of mirror materials. We can calculate specular GI the same way. Here is the same thing. You can see the highlights on the curtain from like a porcelain-like material that has a specular part in its lighting model. Here is another example of specularly lit scene. And here's an example of a combined diffuse plus specular in-game. This implementation is even faster than our previous one. So basically, all global illumination solutions converge to the same result. Because the correct result is known. That's why I'm not even showing you side-by-side comparison, because if two global illumination algorithms are correct, they should produce the same image. The question is how quickly they produce this image. And this algorithm it just scales so much better than everything else I've ever seen. It scales even better than our previous one, even though the previous one was pretty good, honestly. So yeah, this property of absolute double dipping and double exponentials when each cascade.
How much do we still have left of the talk? I really have to go soon. How much is left?
Captures twice more rays for twice less speed is a totally OP exploit in reality. And you are the first audience to learn about it. Thank you. Thank you very much. I hope we have some time for Q&A from Octavian here.
That was insane. Like, a lot of knowledge. We're going to watch the Q&A later. There's a lot of stuff that you can use and learn to apply to your own engine. And I think the best one, in my opinion, was the global illumination and the lava part, where we have the shader toy from. And for the YouTube guys, thank you for watching on YouTube.